the dinner of yesterday was taking more time than expected, so as usual, we are in Italy, so it's expected delay. The Italian knows, yeah, I know that for you maybe it's not expected. So yeah, I know that our intention was to sleep more, but I'm sure that we will enjoy this speech by Sridhar Mahadevan. And let me briefly introduce him, because I don't want to stall too much time. So Sridhar worked as a professor at the University of Massachusetts for 17, 18 years. And he is now moving to industry, and he is the director of the data science laboratory at Adobe Research. And we invited him because of his broadly recognized expertise in machine learning. He has more than 150 papers, and we are talking about top conferences and journals. He is a fellow of AIIA since 2014, and the previous year, 2018, his paper entitled "Imagination Machines: A New Challenge for Artificial Intelligence" received a prestigious prize by AIIA, the Blue Sky Best Paper. This is a prize that is assigned for presenting new ideas, new vision, something that can stimulate the research to push new directions, somehow to leave the comfort zone. Now, as some of you know, at least those in the program committee, this year we asked a suggestion to who we should invite. We received some nice support for the candidate, for the nomination of Sridhar, and I would like to quote this. So I attended an incredible, inspiring tutorial titled "Imagination Science Beyond Data Science" at AIIA 2019. The tutorial was mind-blowing and really deep, inspirational and foundation. So the expectation is high, at least for me. And I really like this notion of imagination science. So from what I understood, today's talk is in this context. And the title is "Machines Who Imagine, Envisioning the Future of AI Beyond Data Science." And this should give us an idea of what AI can do, not just to analyze the past history, but also to understand the future. So please welcome Sridhar, and the stage is yours.
So I'm delighted to be here. I don't know if the mic is working. Yes. Push. Hello? Yeah. Okay. Good. Thank you, Mario, for inviting me and for the wonderful excursion yesterday. It was a good exercise, and so. I've been in AI for a very long time, so I want to give you a little sense of some of the things I've done before and the context in which I'm working on some ideas today. AI has come a very long way, and when I started, it was a very sort of essentially what we call a blue sky or a moonshot enterprise. I was actually studying to be an electrical engineer because I thought it was a safer thing to do. Computers, when I started, were not things that you carried. If a university was very rich, it could afford one computer, which would occupy a whole building. It used to be called the computer center, and you would program a computer with a big stack of punched cards. That's how I started, and it didn't seem like it was a very interesting field. The first course I took in computer science was Fortran programming. I don't know if any of you know Fortran, but it was one of the old languages. And I said, this doesn't look like a very interesting field. So electrical engineering, we were learning information theory, Maxwell's equations. I said, this looks much more interesting. And then I discovered AI, and my life changed. And I said, okay, looks like I need to do graduate work in computer science. So I went to the U.S. and I was very lucky to work with Professor Tom Mitchell, who was one of the founders of machine learning. And through him, I met a lot of the original founders of the field. And so my life changed in a very good way. And actually, I was in Italy more than 20 years ago because the machine learning conference was in Bari in 1996. Were you there? Oh, you were very young. Oh, it's your city. Okay, so I came for that, and it was interesting experience. We loved Italy, so we were always looking for an opportunity to come back. And so when Mario asked me whether I would be interested, I said yes. And plus, I have to admit that one of my favorite, after dinner drinks is something that comes from Calabria. It's called Anisette di Calabria, which I haven't been able to find in many places. But the closest I can find is Sambuco, but it's not quite the same thing. So maybe before I leave, I'll get to taste it here again. Okay. So this is the book that got me into AI. I don't know if any of you have read this book. I read it as a very young student when I was in my early 20s. Those days you didn't have the internet, you didn't have the web. The only way you found a book was you went to the library, or you went to something strange that they don't do these days. They were called book fairs, and when you go to a book fair, you'll see lots of different books. So I went to a book fair in New Delhi, the capital of India, and I discovered this book. It's not an easy book. It's 800 pages, but it was the first book by Doug Hofstadter. He won the very prestigious Pulitzer Prize for this book in nonfiction. It's about three very creative individuals. Kurt Gödel, on the left, was a famous mathematician who proved the famous incompleteness theorem, showing that there are statements in logic that you cannot prove to be true or false if the logic is powerful enough to include arithmetic. This shattered the hope that mechanical computation, would be able to answer any question. M.C. Escher was a famous Dutch artist whose paintings had very interesting sort of visual illusions, and I'll talk more about that painting in a bit. And Johann Sebastian Bach is one of the founders of Western classical music. So, but the book was really a lot about AI, and reading this book made me change my mind about computer science, and I decided to write my own machine learning program in 1982. But the field was very small then, but I was lucky enough to come to the US and work with Tom Mitchell. My first machine learning meeting had 40 researchers. That was the size of the community. Now, I think the main machine learning conferences like NeurIPS have over 10,000 attendees, and I'm told the registration sells out in 2 minutes. And there's literally, I'm waiting for the day when there will be a black market in NeurIPS registration tickets. So it's an amazing change in the field. So largely, machine learning and AI is all about data. This is transforming the field for many reasons. One being that it's now possible to collect vast amounts of data and analyze this data. So two things have happened. One is, we all carry devices like this. For many people, this is the only computer they will ever own, and these are getting incredibly powerful, but they are amazing data collection devices. So there are billions of these devices collecting data all the time, and this data has a lot of information in it, and this can be used in both, as you know, good ways and not so good ways. And compute power and things like cloud computing have totally transformed the field. So AI has been able to build on these successes, and algorithms that were developed a long time ago, like the backpropagation algorithm that was developed in the mid-1980s, and actually there's research showing that it was developed quite a bit before that. But I was at Carnegie Mellon, where I took the first neural net class with Jeff Hinton in around 1987, I think. And he was a young assistant professor then. So 30 years later, that algorithm and that technology has now come to dominate AI, largely because we now have the data and compute power to make things happen. So AI has also become geopolitical. So I don't know if you've seen this book by Kai-Fu Lee on AI superpowers and the rise of countries like China, who has decided to invest a lot of funding in AI. If you go to AI conferences, you will find a lot of papers now from China, a lot of attendees from China, and a lot of companies advertising from China. And so it's clear that AI has become truly international. There's a very significant amount of AI activity in Canada, in Europe. So a lot of countries have realized the power of AI. And this quote by Kai-Fu Lee, if data were petroleum in the AI era, China is going to be the new Saudi Arabia. So this is the field we find ourselves in, and I'm not going to really talk too much about this because I know most of you already know this. I will say a little bit about what Adobe does in this space, because I'm now at Adobe Research. Since they pay my salary, I feel some obligation to say a little bit. But I want to tie it into what I'm going to talk about. So Adobe has 3 lines of businesses. These are the document cloud. So most of you have used PDF, so you know about Adobe PDF, which is the standard for distributing digital content in text. There's the Adobe Creative Cloud, which if you're a serious photographer, you might have used Lightroom or Photoshop, or if you are into making movies, maybe Adobe Premiere. So Adobe markets software for the creative professional, and it's a world leader in this area. Finally, the part of Adobe that a lot of people don't know about is the Adobe Experience Cloud. We manage just about as much data as Google or Amazon or Facebook or Microsoft does, but that we're not in the news, and to me that's a good thing. We're not subject to many of the things that have happened. So the data that Adobe analyzes comes from many sources. Virtually every Fortune 500 company in the world uses Adobe software to analyze, for example, shopping experiences. If you shop at eBay, if you travel on many airlines, if you fly through Heathrow Airport, we manage content on the web for many companies, including Apple. So if you go to apple.com, Adobe is the one managing Apple's content. So this gives us a vast amount of data to do machine learning. That's essentially what I do in let's call it my day job. I lead a team of researchers where we develop very scalable machine learning algorithms to deal with hundreds of petabytes of data. And so there's significant computer science challenges there. So, but I don't want to spend time talking about this too much. It's a different topic. It's still very interesting. It's one reason I moved to industry from academia, just to get a sense for some of the computational challenges, being able to do things at scale. And so we have a team of people that have, for example, one of our researchers has a PhD in mathematics from Yale. So we tend to hire very mathematically oriented researchers because a lot of the technology we use tends to be things that doesn't come from standard packages, but we have to custom design. So, but I'm here really to talk about the limitations of this paradigm. So are there limitations to this approach? And it should be obvious, but a lot of people don't see this, is that it's not always the case that there's huge amounts of data. So for example, we don't have data on what aliens look like. But that doesn't stop Hollywood from making movies on aliens every year, and people spend tens of billions of dollars to go see these movies. So you don't go there saying, well, this is all fake. I'm not going to spend my money watching this movie. People love movies about science fiction, and the fact that it's not based on real data is not something you really consider. So we had this lovely excursion yesterday, and if you were at the planetarium, there was this big statuette of an alien, right? And so this is imagination. We imagine what an encounter with an alien might look like. If that ever does happen, we have no idea what an alien would look like. One of the last projects I did at UMass was analyzing data from Curiosity. If you might remember, Curiosity is a NASA robot that's right now sitting on Mars. It has a lot of scientific instruments, and it's sending back data to us. So we had several projects funded by NASA and the National Science Foundation on analyzing data from one of Curiosity's instruments. It's called the LIBS instrument, Laser-Induced Breakdown Spectroscopy. It sends back high-dimensional data from essentially zapping rocks with a very high-powered laser. So I used to joke with my graduate students, maybe we'll discover the little green men on Mars that we have always suspected. Of course, we never did. But we don't know what aliens look like, really. But we can imagine, and people imagine all the time. There are other things that we're rapidly approaching an environment where cars will be autonomous, and our cities might have to be redesigned. There's no data for this, right? Right now, if you go to San Francisco, on any given day, there might be hundreds of self-driving cars. But maybe in 5 or 10 years, there might be tens of thousands, maybe hundreds of thousands of self-driving cars. And how would you redesign the city? Do you need traffic lights? How would highways look? Do you need parking lots? This is all something you don't have data for, so you have to imagine these things. So virtually every advance in technology requires imagination, and it's an extremely powerful force. And so how do we actually do this? So this is a paper that, This is the paper that Mario mentioned that I wrote. When I was actually director of the SRI AI Center, which was the reason I moved to the Bay Area. SRI is a very well-known research center just outside Stanford. It used to be called the Stanford Research Institute. They've had an AI center there for more than 4 decades, and a lot of impressive work has come out from SRI, including things like the first mobile robot, Shaky, which you might have read about in an AI textbook, the A-star algorithm, which every routing firm, like for example Uber and Google Maps uses A-star. So when I was asked to direct the SRI AI Center, I took the job, and part of that was developing a new initiative, and I started thinking about how machines can imagine. And the last 2 years have been really going around talking to a lot of people and giving a lot of presentations on this, and discovering that there's a lot of work in this. And so I want to talk about some of that work today. So our ability to imagine is very ancient. It's not new. This is a wonderful figurine that was discovered in a cave in Germany. It's believed to have been carved more than 40,000 years ago. So one of our ancestors took the time to carve this essentially impossible object. It's called Lion Man because it shows a person, a fictitious person, with the head of a lion and the body of a man. Why was the statue carved? It's clear it has no hunting value whatsoever. It's a pure work of art. So from 40,000 years, we've been able to do this. If you went on the excursion yesterday, we went through this open-air museum where you saw art being displayed. And so we have this intrinsic desire to create art. Why do we do this? It's just in our nature to do this. And so we want to ask the question, can machines do something like this? What does it take for a machine to do art? So I want to talk about some of the work that's now starting in this, and maybe what the technological implications of this work might be. So the Adobe Creative Cloud is probably the world's most widely used software suite for the creative professional. So if you walk around Adobe's campus, you will find a lot of mention of the word creativity. So creativity is very much at the DNA of Adobe. And so there's this website you might want to go to. It's called mycreativetype.com. It will ask you a series of questions, and based on your answers, it will classify you into different creative types. If you're curious, everybody here is, I'm sure, a very creative person. We're all creative in different ways. What sort of ways are you creative in? You might want to discover with this on this website. And so this web page says that what creativity is and where it comes from is one of life's greatest mysteries. And so we want to see if AI can shed a little light on this mystery. And so some examples of creative types are dreamer. When I took the questionnaire, it classified me as a dreamer. And one of my colleagues took the test, and he was classified as an adventurer. There's different categories. There's a thinker, there's a producer, and so on. So the kind of questions you get asked are things like, when you go on a trip, do you need a destination or do you need a direction? So based on your answer to that question, you get pegged in a certain way. And questions are like this. It's sort of open-ended. There's actually tremendous literature on creativity. I won't go through all of it, but I will point to two books. One is an old book by Margaret Bowden, who's been talking about models of creativity for a long time. She teaches in England. The other is a very new book that just came out by Professor Arthur Miller, who teaches at UCL. I was just at UCL 2 days ago giving an invited talk. And so this is a wonderful book if you want to get a sense of what is the sort of work today in AI on creativity. So I might use a couple of examples from this book, but I recommend the book highly. It gives a very good overview of all the different research in AI on creativity. And Professor Miller went to talk to all the original researchers. He's an expert on creativity in art and science. So one of the many books he's written on this topic is a book on Albert Einstein and Pablo Picasso. Apparently when Picasso started to work on one of his famous paintings that introduced Cubism, he was part of a reading group that talked, among other things, about Einstein's new relativity theory. So there's some conjecture that Picasso was trying to take this new scientific idea and somehow construct a new art form through this. So this shows the kinds of things that very creative people can do, and what does it take for machines to do something even close to this. So that's what we want to find out. But we're also sort of interested in a more mundane way on, how can we use imagination and creativity to build the future for data science. So for that we have to understand what does data science typically do and how is creativity and imagination different. So data science typically asks the question, what is the world like? So Adobe uses a lot of software for this. For example, the Adobe Audience Manager is a software suite that will analyze, for example, shopping behavior from millions of consumers and give you various ways to understand what your marketing segments are. And so this is saying, what does the world look like now? But imagination is not about the world as it is now. It's about the world as it might be, or the world as it might have been. And also it's about what happens if I change the world in some way, right? So if we're data mining user behavior, we are typically doing standard data science. If we start making interventions like, in the US, for example, next week we have the Thanksgiving break. As part of that is a very big sale day called Black Friday, which is a big shopping event for many companies in the US. They make a significant percentage of their turnover on Black Friday. China just had something called Singles Day, And Alibaba apparently recorded more than $1 billion in sales in the first minute of single stay. In 1 minute, they had a revenue of $1 billion. So that tells you something about consumer behavior. People spend a huge amount of money driven by these kinds of marketing decisions, like having these days. So what if asks, what if we did something and how do we change behavior? And then you need explanations. You need to understand why did something happen. If you did something and it didn't work as planned, why did this happen? So all of this asks questions that go typically beyond what standard machine learning asks. So one of the other important aspects is technology that's now coming to market. So my first job was at IBM Research, and when I got hired, they didn't know what to do with a machine learning researcher like myself, because those were the days before machine learning was a popular subject. So they put me in with a group of robotics researchers. I didn't know anything about robotics, but they said, well, you'll figure it out. And it was the best thing they did. So if you're on, at university and you're looking for a job, my advice is to try to find a job where you don't know what to do and you think you don't have the skills, because if you get out of your comfort zone, typically you will surprise yourself by doing something interesting. That's what happened to me. I ended up in 3 years publishing this book, which was probably the first book on robot learning. It attracted a lot of attention, and one of the chapters in this book was a project at Carnegie Mellon on building self-driving vehicles using neural nets, which is a pretty revolutionary idea for when this was done in the late 80s, because people tried in the beginning to program the vehicle by hand to drive in Pittsburgh, and they used classical computer vision technology. It was a complete failure. At one point, they were so frustrated that when they were driving the vehicle through some of the streets near CMU campus, this is Henry Park, they sort of had an idea to ask the city council if they could paint all the trees red so that it would be easier to tell trees apart. And it just didn't go anywhere. And then Dean Pomerleau was a grad student then, and he said, well, there's this new thing called neural networks. So why don't we try to just learn the mapping? And he did, and for his thesis, he showed the vehicle driving on Pittsburgh highways at 65 miles an hour using neural nets. So this was the first demonstration that machine learning could do something that we couldn't just program by hand. I know this technology is in cars. Tesla offers self-driving. This is the Model S car that actually I can now afford to buy, since I'm paid quite well at Adobe. So I drive this car, and I tried self-driving. It's not fully self-driving. It's sort of a smart, steering, if you want to call it that. But it does change lanes. It does follow traffic. It can take exits. And the technology now is there at Tesla to do full self-driving. They haven't released it yet, but they have videos where it can take you all the way. So my wife thinks I'm completely crazy, but this is the future that we're going to face. One of the problems in building self-driving cars is that you need enormous amounts of data, and it's not clear whether we have enough data. So for example, if you collect petabytes of data on what the road conditions look like, well, maybe you collected the data during the day. What happens at night? So the amount of data you need is insatiable. So you have this problem, right? You collect data during a certain part of the day, but you ask yourself a what-if question. Well, what if I was driving on this road at night when the visual scene looks completely different? So now there's new technology that has been developed, which I'll talk about a little bit, on how to take daytime shots and convert them to nighttime, or to do what's called style transfer. So another example of where imagination technology is powerful. I don't know if you've used apps on your phone, but for example, I could speculate on what I would look like if I shaved my head and became bald, as I threaten to do with my wife every now and then. But now you can use this app, and it'll show you what you look like if you were bald. This is the next generation of cameras will have all of this technology built in. So you take a picture, and you don't want the world as it is, but maybe you want to take a picture of Cosenza. It's very beautiful Cosenza skyline, but then you want to be rendered in a say a Monet style, and the camera will just do that for you automatically, right? So all of this technology will be in cameras, I think, pretty soon. There are other reasons why we want imagination. So, for example, one of the biggest challenges we face as humans is that through our activity, the planet is warming. This is a report that was released by the UN. And the left part of the report is what I would consider traditional data science. We have data collected over a long period on the average warming of the oceans, and the magic number is 1.5 degrees from some baseline reference, at which bad things can happen. Now, the projections are that by the end of the century, we might actually face a future that's much worse than that. There's a book that I've been reading that says the planet might warm by as much as 5 degrees. If that happens, we could see mass extinction, basically. The last time the planet warmed by 5 degrees, much of life was killed. So is this going to happen? Well, the second half is what I would call imagination science, because we don't have data. There are no dots to connect. So a lot of it depends on what we do. And the models are sort of not exactly very accurate. So it's a lot of guessing of what might happen. There's a lot of debate. But that's exactly the kind of problem we worry about, is what should we do? For example, coastal cities might be inundated. One of my colleagues recently moved to take up a job. There's a new AI center in Vietnam. A recent report said much of Vietnam could be underwater in 50 years. So similarly, a lot of low-lying countries like Bangladesh, a lot of coastal cities, Miami, New York, London, could be inundated. But how do we make people change their views, including, for example, the U.S. president, who thinks climate change is a hoax? This is some of the challenges in imagination. So there's this very nice book by Uday Pearl, who you may know about, one of the architects of the modern AI statistical and probabilistic paradigm, who's been arguing for why we need to build tools that go beyond traditional machine learning to tools that not ask how to build a model that fits the data, but how to answer questions about what the world would look like if we make changes to the world, right? So, and this is a very non-technical explanation of his work over the past 20 years. It's called The Book of Why. This is very nice to read. And there's a 3-level cognitive architecture in this book. At the bottom level, you have data science. You have learning by association. You see values of some random variables. You build correlations. And you can do useful things with that. We do this all the time. It's a very useful thing to do. And this is what a lot of Adobe software does. But it's not enough. At the second level, you have causal interventions. You take actions in the world, changes the stochastic dynamics of the world, and you have to understand how to deal with that. And at the third level, you have imagination. You have counterfactual reasoning, where you ask, not what the world. Just another way to think about this is at the bottom, you're asking, what is the world now like now? At the second layer, you're asking the question, what does the world look like if I do this thing? At the third layer, you're asking, what does the world look like now versus what it would look like if I did this thing, or if I hadn't done this thing but had done something else. So you're reasoning about multiple possible worlds, most of them hypothetical worlds. And so this is one of the reasons imagination is extremely important and something we use all the time. So I'm going to briefly talk about a certain model of imagination and creativity that is a synthesis of what a lot of people have been doing. And I want to introduce, maybe if I have enough time, some math associated with it. So roughly, a lot of machine learning revolves around an interaction with a student or an actor and a teacher or a critic. And this interaction often involves some sort of a game. So for example, at UMass, I directed a lab called the Autonomous Learning Lab with my colleague Andy Bartow, from where many of the basic techniques in reinforcement learning were developed, including his work on the actor-critic architecture. This is the architecture that was used by, for example, Google DeepMind in their Go work, AlphaGo, and as I'll show you, one of the most important advances in deep learning recently is based on this actor-critic architecture. The actor-critic architecture involves a very interesting change where you have a student and a teacher, but both are learning. So typically when you take a class as a student, you come to the first lecture and your professor says, I'm going to talk about computer science or whatever the topic is, and you expect your professor to be smart. Well, in actor-critic, it's sort of like you're taking a class and your professor comes in and says, well, I don't know much about the subject just like you, but we're going to learn together. And if that happens, you're going to say, well, I want my money back because this is not what I paid my tuition for. But actor-critic works this way, and the teacher is learning like the students. They learn together, and surprisingly, this seems to work well. We don't fully understand theoretically why this works really well, but it seems to work well, and it's the basis for a lot of work in AI. So the first model I'll talk about is one you might know already, called the GAN model. It's one of the most popular deep learning models by Ian Goodfellow. It's a special case of the actor-critic architecture. And there was this MIT Technology Review article calling Ian Goodfellow the GAN father for inventing GANs. So as you might know, GANs are based on this teacher-student model where the student is the generator producing content. It could be video or text or images of a certain type. And the teacher wants to tell apart content that is real, so the teacher is given real content, say face images, versus fake produced by the generator. In the beginning, the teacher can't tell apart real versus fake. So the teacher is just as clueless as a student, but they learn together in this actor-critic paradigm. And so it's a two-player game. And so the dynamics of this game are interesting. One of my recent PhD students, Ian Gemp, actually spent 5 years bringing a lot of interesting math to this problem. And he's now at DeepMind in London. So I'll talk a little bit about his work and what are the challenges in analyzing this sort of two-player game in GAN models. So in the basic GAN model, you have the saddle point loss function. So the teacher is represented by D, the discriminator. And so what it's trying to do is to make sure it can recognize real data. So it wants to maximize the log likelihood of real data. That's the first term. So if X is sampled from the distribution of real data, real images of faces, say, then it wants to maximize log D of X, so the log likelihood of real data. But it also wants to make sure it can tell apart real data from fake data produced by the generator, the student. That's the second term, right? So G of Z is the student-produced data. Z is a noise variable. So it wants to minimize G of Z. So it wants to maximize 1 minus D of G of Z, or the log likelihood of that. So the student wants to do exactly the opposite, right? The student wants to fool the teacher. So you can imagine the implications of this paradigm for redesigning universities, right? So one of, actually two students of mine proposed a variant of this model, was published a couple of years ago, where you had multiple teachers. Surprisingly, this works a lot better. So the curve on the right shows a training run where the axis is essentially, the vertical axis is plotting probability of telling apart real from fake. So the system converges when the teacher is randomly guessing. So if it converges to 0.5, it means the student can completely successfully produce content that cannot be told apart from real content, right? So as you add more teachers, you can see the convergence improves. And this turned out to be a very useful component of a lot of models in GAN technology. Sanjeev Arora is one of the world's best theorists at Princeton. He's at Princeton University and the Institute for Advanced Study. Wrote a paper analyzing the theoretical convergence of GAN models, where you have multiple students and multiple teachers, multiple generators and multiple discriminators, and the dynamics gets pretty complicated. So what I want to talk about is things that are even more complicated than this, and then how this connects to creativity. So this was a demonstration by NVIDIA, the company that makes computer graphics processors, and they're in the Bay Area. This is a model they call ProGAN, which uses layered series of these teacher-student models. And these are completely fake people, but they look amazingly realistic. This is imagination of a certain kind. It's not particularly creative, although one could debate that. And as you can see, there's sort of interesting uses of this technology that we can only begin to think about at this point. We can also try to bring in knowledge into this process, right? The basic GAN model is very knowledge poor, except for this initial set of data about real images. But we know a lot about faces, for example. So you can try to incorporate this knowledge into generating these images. And this is the work of somebody who's now at IBM Research on what are called causal GAN models. So you add a generative causal model that talks about how gender and age influences the kind of images you see of people. And then you can use this to condition the process of generating fake images. And so we're going to see many more models that look like this. So bringing in classical AI technology on things like Bayes nets, causal models, and I'm sure sometime in the not too distant future we can start writing rules and logic that will help us do these sorts of visual imagination problems better. So how do we handle transfer? It turns out there's a variant of GANs called cycle GAN, where you can, for example, say, we have this painting by Monet. What does the actual scene look like that Monet painted? So you want to convert the Monet painting into a digital image that a camera might have taken. And so you can try to do that. And it seems to work surprisingly well in some cases. And so cycle GANs are now used quite a lot in for example, training autonomous cars. So GANs are probably one of the most important advances in machine learning recently, although we don't understand them theoretically well enough at this point. But one could argue that they're not very creative. So how do we go beyond this technology? So we have to ask ourselves, what is creativity? What is art? And it's not just taking faces and producing new faces, right? That's not what people like Picasso did or Monet. To be creative, you have to be able to do something novel. So if you walked around that tour we had yesterday, you saw a lot of different styles of art. And you can see the artists were trying to be creative by somehow showing things in a new way. How do we get machines to do this? So art is, interesting in many ways. So this is on the right. There's a painting by Jean-Michel Basquiat, who's a painter in the U.S. who came out of the Bronx. He was actually originally a graffiti artist. He died very young, in his late 20s. His art now sells for prices that are close to Picasso and Monet. This particular piece sold for over $100 million in an auction in New York recently, and was bought by a Japanese investor. So you look at this and say, why is this worth $100 million? Well, it's worth $100 million because somebody wants to pay $100 million for this painting. So they asked the person who bought it, saying, why did you pay so much money for this painting? And well, he gave actually a long answer. He said, well, first it speaks to me. I resonate with this painting. So there's an emotional connection. But then he said, I saw that, there was a room full of very smart people all bidding for this painting. And they were all bidding close to this price. And I said, well, Clearly, a lot of people think this painting is valuable. So, maybe as a pure business proposition, it's not a good idea. It's not a bad idea to buy this painting, and maybe in a few years it'll be worth even more. So what is Basquiat trying to do here? This is not a digital image of a face. It's something more abstract, right? How do we do this? How can you get a computer to do stuff like this? So we have to move away from the GAN model to some extent. We can't just, in the GAN, you have samples coming from some complex distribution like faces. You want to produce new samples. This is still classical statistics. How do we move away from this? So imagine that you start getting samples, and your task is to do something new. So for example, if you were learning to be a composer and you wrote pieces in the style of Mozart, they might sound very pleasing, but you will never be a famous composer, right? I mean, that's not what makes you famous. You have to invent a new style. So for example, when Stravinsky wrote his famous Rite of Spring Ballet in Paris in the beginning of the 20th century, the performers were booed off the stage because the audience was used to hearing Tchaikovsky's ballets and very melodious, and here comes this piece that looks completely different, sounds very strange. And yet, it made Stravinsky famous, and that's one of the most famous pieces today in classical music, is the Rite of Spring. So it was a novel thing. So the first thing you have to see is, you have to be able to produce content that looks different from what you were given. So we have to figure out how to do that. So there's this very interesting variant of a GAN. It's called a creative adversarial network. And the way it works is it has two kinds of teachers. It has the teacher that says, I am going to judge the content based on one of the accepted styles. If you give it paintings from different styles, it learns whether a painting is a Monet painting, or Impressionist painting, or Cubist painting, or Rembrandt, or different styles. It's given paintings from many different styles. The second teacher learns if something is art. So the student is now asked to produce art that does not fall within one of the styles. Okay? So it's a little different. So you're forcing the student to be creative by saying, here's art from different styles. Now give me something that's art but not one of these styles. So you can't just do what a GAN does. So the loss function looks a little bit more complicated. I'll just walk you through a little bit of it. The first part of it on the left is exactly the same as the GAN loss function. So you're maximizing the log likelihood of real data and minimizing the log likelihood of fake data. But on the part on the right, what you're trying to do is to encourage the student to produce something that doesn't fall into one of the standard categories, right? So it's a way of sort of doing creativity. So creative adversarial networks are an attempt to produce in a computer the ability to do something novel. So you can it's given data from lots of different styles of painting, and here's what it produces. Now you have to look at this and say, well, would somebody pay $100 million for one of these paintings? Again, that's a question for the person who's going to buy it. But people are starting to buy art created by computers. You might have read about this. There was an auction house that sold a painting made by actually a standard GAN, modified a little bit, which sold for $500,000. It's not bad. I give a version of this talk at Berkeley in Stuart Russell's group. You might know Stuart Russell, who wrote the popular AI textbook. Stuart and I know each other for many years. He was on my PhD committee. And I told Stuart, I'm not an art critic, but this doesn't look like a Basquiat-style painting. And he said, yeah, maybe the Museum of Modern Art in New York would not take one of these paintings, but people use paintings in many locations, for example, in shopping malls, in their homes. And we might be at the point in AI when we can mass produce creative art, maybe not for museums, but for people's homes, or for shopping malls, or for hotels. They can't afford to pay prices for original artwork, but so maybe we have made some progress, right? So I want to take just a few more minutes and talk about some of the underlying computational challenges involved in some of this. So the way you train these models, I'm just talking about deep learning models for now, you use gradient descent. Unfortunately, that doesn't necessarily work well. So I want to show you a little bit of why that's the case. So this is joint work with my student Ian Gamp, who's now at DeepMind. In this actor-critic sort of GAN sort of framework, you have this game between the student and the teacher, and you're trying to find an equilibrium. So if you use gradient descent on both the teacher and the student, it's not necessarily the case that gradient descent is guaranteed to converge to an equilibrium. In fact, it turns out that what you might want to do is move in the direction orthogonal to the gradient. And the way that comes about is to look at the problem not as optimization, but using something more powerful that came originally from physics. And the reason it's important for me to talk about this here is the person who invented the math was an Italian mathematician named Stampacchia. How many people here have heard of Stampacchia? Stampacchia, a very famous mathematician who invented this paradigm called the variational inequalities. And so it was originally for physics. But it turned out that it was discovered by economists about 30 years ago for understanding how to model very complex problems involving games played by tens of thousands of actors, many kinds of games. And the simplest one I can talk about is traffic. So if you think of traffic, well, you have tens of thousands or hundreds of thousands of cars competing for the scarce resources of roads, and how do you analyze a game that's this complicated? You can try to write it as an optimization problem, but it's not easy. And it turns out variational inequalities are very useful. So I'm going to show you how this paradigm can be used to study imagination machines. So GANs are typically done with simultaneous gradient descent. There are quite a few papers, but it doesn't work well. And here's a very simple example of where things can go wrong. This is based on a very simple, two-player game where the equilibrium point is at the center. But going in the gradient direction will just take you around a loop. And that's no good at all. So this brings to mind this famous painting by Escher. It's called Ascending and Descending. It's two groups of monks going around in circles. But the strange thing is that one group of monks is climbing, but they come back to the same point. How can you climb a circular staircase and come back to the same point? The other group is descending a circular staircase, and they're also coming back to the same point. So Escher is playing a trick on our visual system by fooling ourselves to believe that this is possible. It turns out mathematicians study this. It's called homology. So there's interesting work now on computational homologies. So very quickly, since I don't have a lot of time, optimization is minimizing some scalar valued loss function. The simplest one being a convex loss function that, for example, if you did something like a support vector machine, you would get. We understand this really well. There's been 200 years of research on this. The one on the right is what Stampacchia did. It's called equilibration, where you're trying to understand the equilibrium of rigid bodies. It's different. So capital F is a vector field. So the simplest way to think about a vector field is take the scalar function on the left, the little f, and take its gradient. It's Jacobian. The gradient tells you the direction in which the function increases at every point in space. So it's a vector field. So if you plug the gradient of little f for capital F on the right, you get the condition for a local minimum. So variational inequality is just a generalization of this concept. It applies for cases when the vector field is generated by something that does not translate back into the picture on the left. So we can have a non-conservative vector field where there is no corresponding little f objective function. So if you're interested in this, I gave a tutorial at AAAI a few years ago on this technology. and showed how it can be used in lots of interesting things. And I don't have much more time, so I won't, say too much more about this. Should I stop now or? A couple of minutes. Okay. So I won't say too much more, but one of the problems that we analyzed using this is this internet model that one of my colleagues at UMass, who is an expert in this, studied. She's in management science, and this is an economic model of the internet, where you can look at the internet as a very complex game played by maybe millions of agents. And here we're looking at content distribution on the internet. So you have the equivalent of generators at the top that are the service providers. So when you subscribe to a video content service like Netflix or Amazon Prime or Hulu or something else, you have the content providers on the top competing. But then to get the content, the bits, you need transport providers. So these are the people at the middle. So these are your cell phone carriers. So in the US, for example, we have AT&T, Verizon, and so on. In the UK, you have Vodafone, and I'm sure you have similar carriers in Italy. And they're playing a game as well. And at the bottom, you have demand markets, maybe consumers. They're trying to decide which content provider, which transport provider to get, and everybody's playing this game, and you want to analyze the dynamics of this game, right? So it's difficult to do this using optimization, but with variational inequalities, you can solve this very nicely. And what my student did was show how to use a more advanced form of gradient descent, something called mirror descent, to solve very large BI models. So one of the things that we're trying to do that I'm interested in is how do you take these more advanced models and now go back and develop the next generation of GAN technology that can do even more creative kinds of things. So with that, let me stop. Thank you. Yeah, actually, I've seen that paper. Yes. Yeah. So I'm glad you mentioned that. So there is a very active group of researchers who've been studying creativity for a long time. This is the computational creativity community, and I've been reading through some of that literature, including conceptual blending. I won't judge myself to be an expert in this field, so. I think there are a lot of insights from that work, but I would say a lot of that work I have seen is not yet very rigorous. There are interesting insights. So a lot of the creativity books, for example, are like this too. There are lots of interesting examples, but what I am looking for is to understand if there is a computational principle behind creativity. So I don't know if you've heard of Jürgen Schmidhuber, who teaches at in Lausanne in Switzerland. You might know him because he's the inventor of a very popular deep learning model called LSTM. But Schmidhuber is very interested in creativity, and he has this paper that says, I'll read the title, "A simple principle that explains essential aspects of subjective beauty, novelty, surprise, interestingness, attention, curiosity, creativity, art, science, music, and jokes." Now, this is the most ambitious paper title I've ever read. So I will leave you to read that paper. But, I'm not sure I buy Schmidhuber's argument, but I am of the same motivation, I would say, which is to see if there is some simplicity in this thing called creativity. Schmidhuber was arguing in this paper that it's essentially Kolmogorov complexity. Kolmogorov complexity is this field that says what you want to do is discover the shortest program that reproduces the data. And of course, it's not computable, but you know. So Schmidt was arguing that it's all compression. All art is essentially compression. And to me, that is too simple to be true. So there's this famous statement by Einstein that says everything should be as simple as possible, but no simpler. I'm not sure this is sufficient, but you know, it's what we're trying to do. And so we take ideas and we're sort of saying, well, what is the computational principle here that people are using to do art or music or any of the things that are considered creative? Let me actually say one more thing, which is a different take on this. One can ask the question, you know, should we even be doing this? So I write a popular sort of blog on Quora. I don't know if some of you have seen this, but I get asked a lot of questions. And somebody said, should we even make imagination machines? Most of the things we can automate with AI are things we'd rather not do, or maybe we can't do. But imagination is something we like to do, and we can do it. Given the tendency of markets to efficiency, you know, if these machines can be more imaginative than us, then it seems like it's a recipe for replacing humans. You know, maybe we should not. You know, maybe we should allow machines to put things in boxes, but leave art and creativity for us. So I've been asked this question several times as well, and so this is something to think about. Maybe this is dangerous, right? We are talking ourselves out of jobs, high-paying jobs, perhaps. So you know, this is something that is not a scientific question; it's more like an ethical question. I also recommend this book by Stuart Russell on why he thinks now that AI may be dangerous in ways that we might not be able to control, and that we should ask ourselves the question whether we can control these systems, and how we should redesign AI so that we build systems that are guaranteed to be what he calls human compatible. So there's a lot of other issues here about, you know, what might happen if we're successful. Sometimes we don't think about this, but it's important. Yeah, no, I agree. I mean, I think, technology tends to be something that you could do good things with and not so good things with. And I think in the long run, the benefits of imagination machines will outweigh the risks. And one of the, last month I was at the U.S. Naval Academy in Annapolis. You might not know, but the U.S. Naval Academy is the oldest defense training facility for the next generation of leaders in the U.S. Navy. And they had a day-long symposium on the promise and risk of the AI revolution. And so I gave the opening keynote. And there were a lot of panelists through the day. And they were talking about the risks of AI technology. And the question is, will AI technology will be used to produce autonomous intelligent weapons? And there's a campaign, you might have seen this, that asks people to sign a letter saying, we will not use AI technology to build the weapons. And in fact, this has been an issue at large software companies like Google recently. I didn't sign this letter because, to me, I think it's futile. Once the technology has been developed, it's going to get used. And we should try to control it. But thinking that it will not be used is really wishful thinking. I mean, the best analogy I can think of, which is actually something Stuart quotes in his book, is nuclear technology. When the atom was first split and people realized the tremendous power inside an atom, there was talk about getting energy from atomic reactions. And Rutherford, who was one of the architects of nuclear physics, said, this is moonshine. You'll never be able to get energy from atoms. And there was an article that appeared in the local newspaper, I think that was the Times of London, describing what Rutherford said. And one of the physicists who discovered or invented nuclear fission was read the article in the morning and went for a walk in the afternoon. And as the traffic light changed and he crossed the street, he discovered how to do nuclear fission. So in one day, the problem was essentially conceptually solved, and he filed a patent the next day. And within a decade or two, we had atomic weapons and we had nuclear technology. So sometimes what we think of as impossible is not really impossible. It can happen much quicker than we imagine. So AI is this revolutionary technology that is now at the brink of changing all our lives in ways we will not even be able to comprehend. And it's an exciting future. For those of you who are young, it's a future you will face more than I will. And you will see the end game. I hope it's a good end game. So. I'm here with my wife, so I am subject to higher authority, but. Sure, I'm fine. Yeah. Yeah, that's a good question. I mean, explainability is now a very important area of research in AI, particularly since deep learning models are being used everywhere. For example, there was this unfortunate accident with Uber in Arizona where a pedestrian was killed. So whenever there's an accident like this, the first question that gets asked if it's a human driver is what happened? Was the driver drunk? What you need an explanation. And if autonomous software will cause a vehicle to kill someone, who's responsible? And so explanations are critical in areas where technology is being used for example, a lot of medicine will be automated just because the cost of delivering healthcare is prohibitive in many areas of the world, and so AI technology will be used to do many things. And so you want an explanation of why a decision was made. And there are people working on this. There's two views. One is it's an important area. We should actually come up with a good solution, and there are ways of trying to take the weights in neural networks and produce something that comes like an explanation. It's still not yet, I think, at the point where it can give us satisfactory results. But there's another school of thought, and this includes people like Jeff Hinton, who has said this is all nonsense. He doesn't believe that humans can explain their decisions. So, not always. So he says, it's this paradox, right? You pay a lot of money for an expert. I don't know, maybe a stockbroker or a physician, or somebody else who says whose time is valuable, and you get a small percentage of the time. You see this expert, and within 1 minute or 2 minutes, he or she tells you something, and you say, "Wow, I paid all that money for 1 minute of this person's time." But in reality, you've paid that money because this person has been doing this for many, many years. And so can they really explain what it is that makes them suggest something? And so Jeff Hinton has argued, we can't explain many things that we do. So it's not clear whether explanations will always be successful, or whether even we can explain things. So ultimately, yeah, thank you.